Welcome back to our next video. In this video, we will be looking at the Born-Haber cycle. So this cycle, it comes under the broader topic, energetics, right? So it has to do with energy changes. But in this video, I will just be constructing the Born-Haber cycle. We will do the calculations in a separate video. So when this video is finished, you should be able to construct Born-Haber cycles accurately for whichever ionic compound you are given. So if this is your first time coming across the Born-Haber cycle, what this cycle does, as the name suggests, Born-Haber, well, not as it suggests, but Born-Haber, that's the name of the scientist that came up with this cycle. So what this cycle does is basically show how ionic compounds, so it's a proposal of how ionic compounds may be formed in a stepwise manner. If you remember ionic bonding, when you did that, it just shows the transfer of electrons from the metal to the non-metal. And then you get your cations and your anions as a result. But what this is going to show is a different approach, a stepwise process to forming that ionic compound. And we will look at a series of enthalpy changes that occurs. So on a Born-Haber cycle, you must have enthalpy of formation, enthalpy of atomization, ionization, electron affinity, and lattice formation. As I construct the diagram, we will look at what each of these are. But the definitions are already here, so you can pause the video and you write it off. All right, so to start the process, let us quickly just look back at what would happen in ionic bonding. So in an ionic bond, you would have your metal. So for example, all right, so let us look at sodium chloride. So as you know, the atom of sodium, atomic number is 11. Therefore, the electronic configuration would be 2, 8, 1. And metals, they will lose their valence electrons. So sodium, when it forms a bond, it would lose 1 electron. So if we're looking at the bonding in sodium fluoride, fluorine atomic number is 9, electronic configuration is 2, 7. Fluorine, the non-metal, it will want to gain 1 electron to complete the second shell. So all we would normally do in the shortened version, we draw the valence shell. So sodium, it has 1 electron on its valence shell, and fluorine has 7. So as we know, sodium must lose 1 electron and fluorine wants to gain 1 electron. So we will transfer 1 electron from sodium to fluorine. So once this happens, The new electronic configuration for sodium would now be 2,8 because it lost the 1 electron on the third shell. And for fluorine, it would also be 2,8 because it gained 1 electron from sodium. Now, whenever an atom loses an electron, loses or gains an electron, ions are produced. If the atom loses electrons, it forms a positive ion. So the sodium atom, well, it's no longer an atom, but the second shell is what it has now. That second shell, as we know, it would have 8 electrons on it. If the atom loses 1 electron, it will have a plus charge. And the amount it loses, whether 1, 2, or 3, that will be the charge on the ion. It essentially has 1 more proton than electron. So it has 1 extra positive charge. Two, 4, 6, 7 electrons, plus it gained 1 electron from sodium. Right, so that's 8. If it gains an electron, it will have an extra negative charge. So these are the two ions that produce the compound sodium, or that are in the compound sodium fluoride. You have a sodium ion and a fluoride ion. So this is what you're accustomed to from ionic bonding. Now, the Born-Haber cycle is going to propose a stepwise process, right? Not just showing the transfer of electron from sodium to fluorine. So what it starts out with, the Born-Haber cycle, it starts out with the elements in their standard state. So sodium exists as a solid in its standard state. Fluorine is a diatomic gas, F2. Now, the Born-Haber cycle, right, it consists of two routes, what we call a direct route and an indirect route. So the direct route is showing the enthalpy of formation. So if you have read the definition for the enthalpy of formation, it is the formation of 1 mole of a compound from the elements in their standard state. So we're forming 1 mole of sodium fluoride. Now, each of these processes have some energy changes associated with them. Now, this topic, as I said, it comes under energetics. So by the time you would have reached the Born-Haber cycle, you would have remembered, or you would have covered exothermic and endothermic reaction. So on an energy profile diagram, right, once the arrow is pointing upwards, That means it is an endothermic process. So down here, you would have the reactants. Here, you would have the products. On the y-axis, it's energy. And this is the course of the reaction, all right, or the progress of the reaction on the x-axis. So in an endothermic reaction, the products have more energy than the reactants. So energy is absorbed. So once the arrow is pointed up, it means it is an endothermic reaction. Once the arrow is pointing downwards, it's an exothermic process. All right, so the Born-Haber cycle is essentially an energy profile diagram showing the different energy changes associated with forming the 1 mole of the ionic compound. So the fact that this arrow is pointing downwards tells you it is an exothermic process. So let's continue. All right, so sodium plus fluorine will form sodium fluoride. This is the direct route. No, remember for the definition, so this part here, it is showing the enthalpy of formation. So you would have delta H F for enthalpy of formation, or standard enthalpy of formation. So you should also have the little symbol at the top. But it should have like a little circle with a line, a horizontal line at the top. Now, if you look at this sodium fluoride here, it has 1 fluoride ion, 1 sodium ion. I can just say 1 sodium, 1 fluorine. But if you look here, fluorine exists as a diatomic molecule, so F2. Now, this is just like an equation. If you look at it, sodium reacts with fluorine to give you sodium fluoride, NaF. All right. But it's just because it's an energy profile diagram, the arrow must point downwards to represent exothermic or upwards to represent endothermic. Now you have to remember this is representing the standard enthalpy of formation. And if you check the definition, it is dealing with the formation of 1 mole of your ionic compound. So if you try to balance this equation, you cannot say you have 2 fluorine here, so you are going to put 2 in front of it. This would make it 2 moles of sodium fluoride. But by definition, we are forming 1 mole of the ionic compound. So what that means, you cannot put any number in front of sodium fluoride. So you have to adjust this so that it becomes 1. So to do that, we put a half in front of it. All right. So you essentially now have 1 fluorine on this side. 2 times a half, that's 1. So you have 1 fluorine on this side and 1 fluorine over here. 1 sodium on this side and 1 sodium on this side. So at the start, you must have half F2. Good. So for the direct process, you have to balance the atoms. But remember, whatever compound you have here, you cannot put any number in front of it because you must get 1 mole. So you have to make the adjustment to these here. to fit the compound. Now, as I said, you have two routes, the direct route. Clearly, this is not the stepwise process because it is just showing the elements in the standard state forming the ionic compound. This has some calculations associated with it. As I said, we will do the calculations in a separate video. For this video, I just want you to know how to construct this diagram. So we start with the direct route. Now let's move on to the indirect route. Right, so first now, if you remember, in order to remove an electron, right, from an atom, it must be in the gaseous state. Sodium is a metal. We know metals exist as solid in their standard state. So if we want to remove an electron, before we can do that, it must be a gas. So we have to first convert our metal from a solid to a gas before we can think about removing an electron from it. So the first process in our indirect route now. So this route going up, that's our indirect route. And the first thing we want to do is convert our metal from the solid state to the gaseous state. So it's now sodium in the gaseous state. We are not touching the fluorine yet, so we are going to put it back as is, which is half F2. Try to make it go on the half F2. Right? Now converting it from the solid to the gas, that is the enthalpy of atomization. You would have read the definition before we reach this part. I'm just going to put the ATM. Now, once the sodium metal is a gas, we can go ahead and remove an electron from it. So let's just look back to the left-hand side. In ionic bonding, the metal transfers electrons to the non-metal. But as you should know by now, we cannot take an electron from the metal in the solid state. We convert it first to a gas. Once we have it in the gaseous state, then we can remove an electron from it, which is what we are going to do now. And remember, when an atom loses an electron, it forms a positive ion. So here, sodium is in the gaseous state. So the next process is to convert it to the sodium ion because we are removing an electron from it. So if the sodium atom gives up an electron, it forms the sodium ion. Fluorine still remains as the diatomic molecule. All right. So remember, when we remove the electron from the atom, that is ionization energy. I'm going to put this symbol for enthalpy change. And I'm going to put I and E for ionization energy. So the indirect route, it starts with converting your metal from solid to a gas, and that's the atomization enthalpy. Once the metal is in the gaseous state, we are going to ionize it. That is, remove an electron from it. That is how we get the sodium ion. Now again, let's go across here. The sodium atom is transferring the electron to a fluorine atom, not a fluorine molecule. Even though you have the half in front, remember the half was just to balance the reaction here. It is still F2. That's a molecule of fluorine. So we need to convert this molecule of fluorine to atoms. So we're converting the fluorine now to atoms. Because if you notice, we have nothing else to do with the sodium. It has given up its one electron. So it's fluorine that needs to accept it now. But fluorine is a molecule, so we need to convert it to atoms. All of these processes we can see are endothermic. They require energy. So we have sodium ion in the gaseous state plus the electron, because remember now we are focusing on the molecule of fluorine. So these two stay as is. So we're atomizing fluorine, converting the molecule to atoms. So here we have the atom of fluorine. We only need one atom of fluorine. As you can see from the formula NaF, we need only one atom of fluorine. So even though it's two atoms of fluorine that forms the fluorine molecule, sodium fluoride is NaF. So we only need one atom of fluorine. Good. So once that is achieved now, if you remember the processes that I said were involved, all right, so this is the atomization of chlorine, not chlorine, fluorine. I'm going to put AT of fluorine. So it's the atomization of fluorine. This was the atomization of sodium. That was first ionization energy. All right. Now we are ready now to transfer the electron from, well, sodium has already given it up. So now the fluorine atom can accept it. So all you need to do is draw the line out a little further. Now we are going to show the fluorine atom accepting the electron. Again, when atoms gain electron, they form negative ions. So at this point, we have the sodium ion and the fluoride ion, both in their gaseous state. And just remember, this is a gas. Right? So here is like, remember, these are like equations, but it's an energy profile, the diagram. So what this is saying, you have sodium, or you can ignore this sodium at this point. Let's focus on what happened to fluorine. The fluorine atom gained an electron to form the fluoride ion. So that is what happened at this point. The fluorine atom gained an electron to form the fluoride ion. Then finally now, the sodium ion. So the final, all right, let me just write this here before I continue. So right here we have electron affinity. So this is the enthalpy. I'm going to put EA for electron affinity. So electron affinity is when an atom gains the electron. So fluorine atom is gaining the electron. First, electron affinity is an exothermic process. So as you can see, the arrow is pointing downwards. If it had gained 2 electrons, we would have drawn a second arrow going up because the second electron affinity is exothermic. So only the first one is exothermic. The others are endothermic. So what you're going to do now is draw this line going out, and they're going to draw a line from the sodium ion plus fluoride ion, come straight down. And this is called the lattice enthalpy. So we are from, as you know, ionic compounds are lattice, right? Crystals are, can say, lattice. So it's the formation of sodium fluoride. So the energy associated with this is the lattice enthalpy. I'm just going to put LAT. So delta H, that's for enthalpy change. All right. Now, all of these processes has a certain number associated with it. All right. So we will do a simple calculation, but I will leave that, as I said, for our next video. So this is the Born-Haber cycle showing the formation of sodium fluoride. So I'm just going to draw, I'm going to highlight something in red. So the indirect route starts from the atom in their standard state and goes all the way around. Back to where you get the ionic compound. In this case, it is sodium fluoride. And the direct route is simply going from the atoms in their standard state to the compound. So this is the indirect route. Let me just put that there. Indirect route. So this is the Born-Haber cycle for you. I'm going to put two. I'm going to stop the video here. But before I stop it, I will give you 2 of them to try, and I will work it in part 2. So this is part 1. But let me just point out something before I close the video. I'm just going to show you what would happen if the atom gained 2 electrons. So let us say it was oxygen. All right, so I'm going to start from this part. So let's say the metal, it gave up the 2 electrons that oxygen requires. So the first electron it gains, that's an exothermic process. So you'd have O minus. The second electron, so you'd have O minus plus the electron. Remember, you would have a metal ion here. I'm just going to put Y plus, or Y2 plus if it is a metal in group 2. All right, so the Y2 plus, that is to represent a cation. So the oxygen would gain 1 electron at this point. So 1 electron would still remain. So when it gains the second one, that's an endothermic process. Second electron affinity. So this one was first electron affinity. So that was first electron affinity, that is exothermic. This is second electron affinity, and it is endothermic. So that is when now you would have O2 minus, because it had gained the second electron. So it would be Y2 plus O2 minus, and then you would have drawn the line, just like you draw it down to the compound, you would have drawn the line coming down. All right. So the oxygen atom must gain 2 electrons. So the first one it gains, that's first electron affinity. And say right O minus, indicating it has gotten 1 electron. And then the second one, we draw the arrow going up, and you have O2 minus. Notice there's no electron here because it gained the second one. Here you have an electron because it had only gotten 1 electron. So that's one way of doing it. If you are required to show the 2 electron affinities, that is what you would do. Otherwise, from doing that, you could do this. So let's say I have Y2 plus the 2 electron plus O. Draw the line going up. So it's Y2 plus O2 minus. So if you look on the internet or some textbooks, they don't necessarily show the first one. Some will show it, but not all of them. So if you see it like this, this is showing both electron affinity in one. So if you notice, my final arrow is pointing upwards because the second electron affinity is endothermic. That is why if you do it like this, you just have one arrow pointed up and not downwards. Because if you just draw one arrow, first one is exo, but the second one is endo. So the overall thing, you draw the arrow going up. So if you want to skip the first electron affinity, this is how it would look. All right. So just draw the arrow pointing up, Y2 plus O2 minus. But if you are showing first and second electron affinity, goes down, then it goes up. And as usual, you will draw the line coming down to meet the compound, the ionic compound YO. All right. So I will do a specific example like this. So I'm going to show you the 2 examples that I want you to do. So it's over here. Let me write it. I wanted to do magnesium oxide. That's MgO. That's the first one. And then probably, let's say Li2O, lithium. Let's do lithium oxide. And then I am going to do aluminum chloride. Or magnesium. We can do aluminum chloride. Maybe I will do 4 of them, maybe not. We'll see. Magnesium chloride came on a past paper. I will search for it. So you can try these. Magnesium oxide. Definitely try magnesium oxide and either aluminum chloride or magnesium chloride. Just to recap, remember the ionic compound here, MgCl2, whichever of these, they're the product. Whatever you have in this starting out, it must match the compound. So you must not try to balance this part. It's the atom in their natural state must be fixed or adjusted to match what the chemical formula is suggesting. All right, so this is the first intro. You can practice these and watch part 2 to see how it is done. So that's where this video ends.